Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we will continue our study of QoS, Quality of Service. In part 1, we covered voice VLANs and Power over Ethernet in the first half, and then I briefly introduced QoS in the second half. Hopefully you understand the purpose of QoS, which is to prioritize certain traffic such as voice and video traffic to reduce the delay, jitter, and loss, and also to ensure it gets the required bandwidth. This time we'll go more in-depth about the terms in exam topic 4.7, such as classification, marking, queuing, congestion, policing, and shaping. Note that you don't need to know QoS design and configuration for the CCNA. As long as you understand the topics I introduce in this video, you should be able to answer QoS questions on the CCNA exam. Here's what we'll cover in today's video. First, classification and marking. This is how routers and switches identify which traffic should be given higher priority. Then we'll cover queuing and congestion management. I already introduced these in the previous video, but let's go more in depth. Finally, shaping and policing. Two ways of controlling the rate at which traffic enters or exits an interface. Watch until the end of the video for a bonus practice question from Boson Software's XSIM for CCNA, the best practice exams for the CCNA. Let's begin with classification. As you know, the purpose of QoS is to give certain kinds of network traffic priority over others during times of network congestion. Classification organizes network traffic, meaning packets, into traffic classes or categories. So why is that important for QoS? Classification is fundamental to QoS. To give priority to certain types of traffic, you have to identify which types of traffic to give priority to. So how can we classify traffic? There are many methods of classifying traffic. Here are some examples. You can use an ACL. Traffic permitted by the ACL will be given certain treatment. For example, it could be treated as high priority, and other traffic which is denied by the ACL will not be given that treatment. This is like how we used ACLs for dynamic NAT. The ACL isn't being used to actually permit or deny traffic, it's just being used to identify certain traffic. There is also NBAR, Network-Based Application Recognition. Sometimes just looking at the lower layer information, such as the TCP or UDP port number and IP address, isn't enough to identify exactly what kind of traffic it is. NBAR performs what's called a deep packet inspection to look beyond the layer 3 and 4 information all the way up to layer 7 to identify the specific kind of traffic. However, we won't focus on methods like these in this video. In the layer 2 and layer 3 headers, there are specific fields used for this purpose, for the purpose of classifying traffic. I mentioned them briefly in previous videos, but finally let's take a look at them. The PCP, Priority Code Point field of the 802.1q tag, can be used to identify high or low priority traffic. Keep in mind that this field can only be used when there is a .1q tag, only when a VLAN tag is added to the Ethernet header. Then there is the DSCP, Differentiated Services Code Point field of the IP header. It can also be used to identify high or lower priority traffic. Okay, let's take a look at each of these. First up, PCP. Here you can see an Ethernet header with a .1q tag, a VLAN tag. The PCP field is in this .1q tag. Here are the fields of the .1q tag that I showed you earlier in the course, and the PCP field is this 3-bit field here. Note that you might also hear this field referred to as COS, Class of Service. Don't mix it up with the entire concept of QoS. COS just refers to this part of the .1q tag. Its use is defined by IEEE 802.1p. So let's see how it has been defined. Well, there are 3 bits, which gives 8 possible values, 0 to 7. This is how they are defined. You probably don't have to memorize all of these, but I recommend remembering 0 for best effort, 3 for critical applications, 4 for video, and 5 for voice. Regarding 0, best effort, what does that mean? Best effort delivery means there is no guarantee that data is delivered or that it meets any QoS standard. It's regular traffic, not high priority. This is the default, by the way. Regular traffic will have a value of 0 in the PCP field. Since we talked about voice traffic a lot in the previous video, let me point out something about 3 and 5. IP phones mark their call signaling traffic as PCP3. Call signaling traffic is used to establish phone calls. However, when the call is established, the actual voice traffic itself, the audio packets, is marked as PCP5. I put the term mark in bold because it's another important QoS term. Basically, to mark traffic is to set the value in the PCP or DSCP fields. Then, network devices look at those markings and use them to classify the traffic as high priority, low priority, etc. So, when an IP phone marks its voice traffic as PCP5, it's because it wants the routers and switches to classify those packets as high priority. Here's a simple network with a couple PCs in VLAN 10 and IP phones in VLAN 20. I want to demonstrate a very important point about using PCP to classify traffic. Because the PCP field is found in the .1q header, it can only be used over the following connection types. First, the obvious one is trunk links. Traffic sent over a trunk link is tagged with .1q, unless the traffic is in the native VLAN, but let's assume the native VLAN isn't being used. However, as I explained in the previous video, voice traffic is tagged as well, even over access links. So assuming the network is configured so that all PCs and phones can communicate with each other, as well as over the external network, which of these links are either trunk links or access links with a voice VLAN? Well, the connections between the phones and the switches are access ports with a voice VLAN. Traffic to and from the phones will be tagged. And these two connections will be trunk links, tagging traffic in VLAN 10 or 20. So, over these connections, devices can mark traffic with a specific PCP value to tell other devices to treat the traffic with a certain level of priority. And devices receiving that marked traffic can classify the traffic as high, medium, low, or whatever priority based on the PCP marking. Let me clarify that in this type of network design, traffic from the PCs is not tagged with .1q here, so it can't have a PCP marking over this link. In addition to that, all traffic between R1 and R2, or between R2 and external destinations, will not have a .1q tag. So traffic over those links cannot be marked with a PCP value. PCP cannot be used to classify traffic. So that's a major limitation of using PCP, a limitation which the Layer 3 classification methods don't have. So, now let's look at how marking and classification is done at Layer 3. In the IPv4 header, there is a byte that is referred to as the TOS byte, type of service. IPv6 also has a byte called the traffic class byte, used for QoS, but let's focus on the IPv4 header. It's this byte here, the second one in the header, after the version and IHL fields. The modern use of the TOS byte consists of two fields, DSCP, Differentiated Services Code Point, and ECN, Explicit Congestion Notification. However, previously this byte was organized differently. Here's the old use of the TOS byte. 3 bits were used for the IPP, IP Precedence field. It was used to mark packets according to their priority, like the PCP field in the .1q header. The remaining 5 bits were mostly defined for some other purpose, but my understanding is that they weren't really used. So, 3 bits once again gives 8 possible values here, just like in the PCP field of the .1q header. However, the current use of the TOS byte, the one shown above, is this: 6 bits for DSCP and 2 for ECN. 6 bits in DSCP allows for a total of 64 values, which gives a lot of flexibility regarding how we can mark and classify traffic in the network. Before going in depth about DSCP, let's take a quick look at IPP. The standard IPP markings are similar to PCP. 6 and 7 are reserved for what's called network control traffic. That refers to traffic like OSPF messages sent between routers. Interactive voice traffic is marked as IPP5. Interactive video traffic is marked as IPP4. IPP3 is used for voice signaling traffic, for setting up and tearing down phone calls. And IPP0 is used for best effort traffic, regular data traffic without any special requirements. So, with 6 and 7 reserved, only 6 possible values remain. Although 6 is sufficient for many networks, the QoS requirements of some more complex networks demand more flexibility. And because IPP only used 3 bits of the TOS byte, and the other 5 largely weren't used, it was decided that an extra 3 bits would be added to IPP to make DSCP, Differentiated Services Code Point. Now let's take a look at DSCP. RFC 2474, which was published in 1998, defines the DSCP field, and then other diffserv, Differentiated Services, RFCs after it, elaborate on the use of the field. With IPP updated to DSCP, new standard markings had to be decided upon. Why is that? By having generally agreed upon standard markings for different kinds of traffic, QoS design and implementation is simplified, QoS works better between ISPs and enterprises because they agree upon the markings that will be used, and there are other benefits too. So, a few sets of industry standard markings were developed. Before we get into it, let me say that it might feel a bit overwhelming trying to remember all of these. I will include flashcards to help you memorize them, but really the only ones you need to remember are some of the more common ones. I'll point those ones out after I've introduced all of the markings. So, you should be aware of the following standard markings. First, default forwarding, DF. This is the marking for best effort traffic, which doesn't have any particular QoS requirements. Then there is EF, expedited forwarding. It's used for traffic that requires low loss, latency, and jitter, which is usually voice traffic. Next is assured forwarding, AF. This isn't one marking, but a set of 12 standard values. Finally, there is class selector, CS, which is a set of 8 standard values. CS provides backward compatibility with IPP. We won't cover QoS configuration because it's not a CCNA exam topic, but let me show you this. I configured a class map called test. When configuring QoS, class maps are used to identify which traffic you want to match. I configured a match statement, specifying that I want to match traffic based on the DSCP value in the IP header. Let's check out the options. At the top is the choice to simply configure the DSCP value in decimal, from 0 to 63. Then below that are the 12 AF values. Notice on the right it shows the binary. For example, AF11 has a binary value of 001010. Under that, there are the CS values. Again, the binary values are displayed on the right. I said there are 8 CS values, but only 7 are shown here. That's because the other one, CS0, is the same as DF, default forwarding, 0000000. Finally, at the bottom is EF, expedited forwarding. Okay, let's look at each of these in more detail. First up, DF and EF. DF is used for best effort traffic. The recommended DSCP marking is 0. So all 6 of these bits will be set to 0. To make things easier to understand as we continue, I'll write the decimal value of each binary bit above. So, standard network traffic like sending an email or downloading a file will probably have 000000 in the DSCP field of the IP header, indicating that it doesn't require any special treatment. Then there is EF, expedited forwarding. EF is used for traffic that requires low loss, latency, and jitter. Typically, voice traffic is marked as EF. The DSCP marking for EF is 46. So this is how it looks in binary, 101110. Okay, so these two are pretty easy to remember. DF is used for best effort traffic, and the DSCP value is 0. EF is used for traffic requiring low loss, low latency, and low jitter, usually voice traffic, and the DSCP value is 46. Now things will get a bit more complicated. So we just looked at default, also called DF, and EF. Now let's look at AF, assured forwarding. AF can be a little tricky to understand, but I'll try to explain it clearly. AF defines 4 traffic classes. All packets in a class have the same priority. A higher class number means higher priority. Their packets will be forwarded with better service than lower priority packets. Then, within each class, there are 3 levels of drop precedence. A higher drop precedence means the packet is more likely to drop during congestion due to WRED. Now, notice that I've set up the 6 DSCP bits a little differently. First up, in AF, this bit on the end is always set to 0. I'm not exactly sure the reason for this. It might just be because the designers of AF decided they didn't need so many values. These 2 bits in red represent the drop precedence, and these 3 bits represent the class. Now, when we write an AF value, it's written as AFXY, with x being the decimal number of the class, and y being the decimal number of the drop precedence. Let's take a look at an example to see how to do it. So we have a binary DSCP value of 001010. As I said, in the AF system, we write it as AFXY, with x being the decimal number of the class, and y being the decimal number of the drop precedence. To do that, we split it up into 2 parts. 3 bits for the class, 2 bits for the drop precedence. So the decimal of the class is 1, and the decimal of the drop precedence is also 1. So this is AF11, or AF11. You can call it whichever you like. Now, really, this is just a 6-bit DSCP number. If I write the normal 6-bit decimal values up top, 1, 2, 4, 8, 16, and 32, we can calculate that this is DSCP10. So, AF11 is the same value as DSCP10. AF is just a set of standard DSCP markings, which is easier to work with than simply having 64 DSCP values with no system of standard values. Let's do some more practice. Now we have binary 001100. What AF value is this? This time it's class 1, drop precedence 2. So it's AF12 or AF12. How could you write this as a normal decimal DSCP value? Here are the values of each bit again. In this case, the DSCP value is also written as 12. So, AF12 is the same as DSCP12. Here's another one. Try to figure it out on your own. What AF value is this? Also, how could we write it as a normal decimal DSCP value? Try to figure it out without me showing you the value of each binary bit. Okay, let's check. Here are the values of each bit. This is AF23 or AF23. Written as a normal DSCP value, it is DSCP22. Hopefully, you were able to figure that out. If not, that's fine. Let's practice a couple more times. This time, we have a binary DSCP value of 011100. What AF value is this, and how is it written as a normal DSCP value? Let's check. Here are the values of each bit. So this is AF32 or AF32. Written as a normal DSCP value, it is DSCP28. So AF32 is the same as DSCP28. Okay, here's one more for practice. Again, what's the AF value, and how can you write it as a normal DSCP value? Let's check. So a class of 4 and a drop precedence of 3. So this is AF43 or AF43. Written as a normal DSCP value, it is DSCP38. So AF43 is equivalent to DSCP38. By the way, within AF, 43 is the highest value. There is no class 5, 6, or 7. Okay, so you should be able to convert between these AF numbers and DSCP values. If you want a quick way to calculate it without writing out the binary every time, here's the formula. 8x plus 2y. Again, the class is x and the drop precedence is y. The reason for this is that 8 is the lowest value of the x portion, and 2 is the lowest value of the y portion. So to calculate it, it's 8x plus 2y. It's always best to understand the binary underneath it all, whether you're learning IPv4 addresses, subnetting, IPv6, matching with ACLs, QoS, whatever. But after understanding the binary, it's also nice to have some shortcuts like this, 8x plus 2y. So here's a summary of all of the AF values. 4 classes with 3 drop precedence values each. So within these AF values, traffic marked as AF41 gets the best treatment. It's in the highest priority class, but has the lowest drop precedence. On the other hand, traffic marked as AF13 gets the worst treatment, being in the lowest priority class with the highest drop precedence. I will include flashcards for all of these to test that you can convert them from the AF values to the regular DSCP values. I'm not expecting you to memorize them, but you should be able to calculate the DSCP value of a given AF value. Okay, that's all for AF. I hope my explanation was clear. If not, feel free to ask questions. Finally, let's look at CS. Fortunately, CS is actually quite simple. CS, class selector, defines 8 DSCP values for backward compatibility with IPP. How does that backward compatibility work? The 3 bits that were added for DSCP are set to 0, and the original IPP bits are used to make 8 possible values. So here's the DSCP field again. Notice that the 3 bits on the right are set to 0, and the 3 bits on the left, the original IP precedence bits, can be either 0 or 1. Here are the decimal values of those 3 bits, 1, 2, and 4. So, IPP gives us values from 0 through 7. The equivalent values in CS are CS0, CS1, CS2, 3, 4, 5, 6, and 7. Very simple. Now you should also know the decimal DSCP value of these. Although CS is a way of organizing the DSCP field into a set of 8 values, they are still DSCP values. Fortunately, it is quite simple to convert them. It's just 8 multiplied by the CS number. CS0 is 0, CS1 is 8, CS2 is 16, CS3 is 24, CS4 is 32, CS5 is 40, CS6 is 48, and CS7 is 56. Okay, that's all for CS. Quite simple. Okay, so we've got DF, EF, AF, and CS. How are we supposed to take those values and actually use them? RFC 4954 was developed with the help of Cisco to bring all of these values together and standardize their use. Many specific recommendations are given in the RFC, but here are a few key ones. Voice traffic is marked as EF because it requires very low delay, jitter, and loss. Interactive video should be marked as AF4X, meaning AF41, 2, or 3. Streaming video is marked as AF3X. High priority data is AF2X, and best effort data is marked as DF, a DSCP value of 0. There are many more recommendations given within the RFC. Do a Google search for it if you're interested. However, in the end, it's up to the engineer designing the QoS policy of the network, which traffic will get which markings. These are just standard recommendations. Okay, let's move on to take a quick look at the topic of trust boundaries. The trust boundary of a network defines where devices trust and don't trust the QoS markings of received messages. If the markings are trusted, that means the device will forward the message without changing the markings. But if the markings aren't trusted, the device will change the markings according to the configured policy. So, for example, let's say the trust boundary is here at switch 1. Phone 1 sends a message marked as EF and COS5 to switch 1. Note that COS is referring to the PCP field in the .1q header. You may hear it called COS5 or PCP5. You should be familiar with both terms. Anyway, switch 1 doesn't trust the markings from phone 1 because it's from outside of the trust boundary. So perhaps it changes the DSCP marking to DF and the COS marking to 0 before forwarding it to R1, which forwards it on to R2 with just the DF marking because there is no .1q header. Now, this configuration isn't ideal. Usually, it's best to trust the markings from an IP phone, because we want its traffic to be high priority anyway. If an IP phone is connected to the switch port, it is recommended to move the trust boundary to the IP phone. This is done via configuration on the switch port connected to the IP phone, by the way, not directly on the phone itself. So, if a tech-savvy user is able to mark their PC's traffic with a high priority marking to get faster service, the marking will be changed according to the configured policy. But traffic sent from the phone itself will be trusted by the switch. In this case, if phone 1 sends an EF and COS5 marked message, switch 1 will trust those markings and not change them. On the other hand, if PC2, for example, sends an EF marked packet, the switch should not trust that, and for example, it might change the EF marking, DSCP46, to DF, DSCP0. We don't want data applications on the PC being treated with the same priority as the voice traffic from the phones. Okay, that's all for trust boundaries. You don't need to know how to configure them for the exam, but just be aware of the concept of trust boundaries and how they work. Okay, that's all for classification and marking. Now let's move on to queuing and congestion management. I already introduced it in the previous video, but there's a bit more to be covered for the CCNA. For review, when a network device receives traffic at a faster rate than it can forward the traffic out of the appropriate interface, packets are placed in that interface's queue as they wait to be forwarded. When the queue becomes full, packets that don't fit in the queue are dropped, and this is called tail drop. RED and WRED, which I already mentioned, drop packets early to avoid tail drop. Here's the image I showed last video. The router is forwarding packets in an FIFO manner, but the queue gets full and packets start getting dropped. RED or WRED could help avoid this by dropping packets earlier. However, an essential part of QoS is the use of multiple queues, not just a single queue. And this is where classification really plays a role. The device can match traffic based on various factors, for example the DSCP marking in the IP header, but also many other things, and then place the traffic in the appropriate queue. However, the device is only able to forward one frame out of an interface at once, so a scheduler is used to decide which queue traffic is forwarded from next. Prioritization allows the scheduler to give certain queues more priority than others. So this is where the power of QoS really becomes clear. Here's that same example as before. However, this time, let's say the router's interface forwarding the traffic has been configured with multiple queues. Here's how it works. Ingress traffic is received by the router. Ingress just means incoming traffic, traffic entering the router. Then it performs routing, meaning it decides which interface to send it out of, as well as other things like NAT if necessary. Then it classifies the traffic, and places it into the appropriate queue. In this case, there are 4 queues, and traffic is classified and placed in a queue, depending on, for example, the DSCP marking. Then the scheduler decides how much traffic to send from each queue, in which order, and the router forwards the traffic one packet at a time. This is an oversimplification, but it's basically how it works. After the router decides which interface to forward the packet out of, it is classified, queued, scheduled, and then transmitted. A common scheduling method is weighted round robin. Round robin means that packets are taken from each queue in order, cyclically. And weighted means that more data is taken from high priority queues each time the scheduler reaches that queue, so those queues get higher output. Next, here's a term you definitely should know. CBWFQ, class-based weighted fair queuing, is a popular method of scheduling, using a weighted round-robin scheduler while guaranteeing each queue a certain percentage of the interface's bandwidth during times of congestion. So let's put these together. Here's the process again. Classify the traffic, place it in queues, schedule it, and transmit. The device is using a weighted round-robin scheduler, sending a certain amount of traffic from each queue in cycles. On top of that, each queue gets a guaranteed minimum amount of bandwidth, even when the queues are congested. So this is getting a lot more advanced than just a single output queue, but it's still not ideal. Specifically, it's not ideal for voice and video traffic. Even if the traffic receives a guaranteed minimum amount of bandwidth, round robin can add delay and jitter, because even the high priority voice and video queues have to wait their turn in the scheduler. To solve that, we can configure LLQ, low latency queuing. LLQ designates one or more queues as strict priority queues. Strict priority means that if there is traffic in the queue, the scheduler will always take the next packet from that queue until it is empty. This is very effective for reducing the delay and jitter of voice and video traffic. As soon as traffic enters the priority queue, the scheduler will forward that traffic. So here's that same diagram, but this time the top queue is a strict priority queue. Currently, there is traffic in the queue, so the scheduler will send all of that traffic before continuing the weighted round-robin scheduling of the other queues. But there's a potential problem here. LLQ has the downside of potentially starving other queues if there is always traffic in the designated strict priority queue. The other queues might never get a turn to send traffic. Policing, which I will cover in the next slide, can control the amount of traffic allowed in the strict priority queue, so that it can't take all of the link's bandwidth. Okay, so in this section, we expanded on the idea of queuing introduced in the previous video, and examined the use of multiple queues. A router classifies traffic, for example by looking at the DSCP value, then places it in the appropriate queue. The scheduler, for example using weighted round-robin logic, forwards packets from each queue in a cycle. With the addition of LLQ, a strict priority queue can be used to immediately forward high-priority packets. And by the way, within each of these queues, congestion prevention tools like RED or WRED can be used to avoid tail drop if that queue becomes full. Okay, here are the final topics for today: shaping and policing. At the CCNA level, you basically just have to understand what these two QoS functions do, so I'll summarize them in one slide. Traffic shaping and policing are both used to control the rate of traffic. In the previous examples of queuing and scheduling, we assumed that the interfaces are operating at full capacity or beyond full capacity, which is why packets need to be queued. However, there are situations in which it is desirable to limit the rate of traffic to below the actual maximum capacity of the link. Shaping buffers traffic in a queue if the traffic rate goes over the configured rate. So this is the same concept I just demonstrated. However, instead of the actual capacity of the link being the limiting factor, it's a maximum traffic rate configured on the link. Policing isn't as polite as shaping. It drops traffic if the traffic rate goes over the configured rate. However, there is some flexibility. Burst traffic over the configured rate is allowed for a short period of time. This accommodates data applications which are bursty in nature. Instead of a constant stream of data, they tend to send data in bursts. Just like the policed data rate, the amount of burst traffic allowed is also configurable. And in both cases, classification can be used to allow for different rates for different kinds of traffic. Now, why would you want to limit the rate traffic is sent or received? To demonstrate one common case, here's a sample network. A customer router is connected to an ISP, Internet Service Provider router. The customer configures shaping outbound on the G00 interface of the router, and the ISP configures policing inbound on the G00 interface of the ISP router. Can you think of a reason why this might be done? Although the physical interfaces are gigabit Ethernet, 1000 megabits per second, perhaps this customer is paying for a 300 megabit per second connection. So the ISP says, you paid for a 300 megabit per second connection, so I'm going to police incoming traffic to 300 megabits per second. The customer then decides, if I send traffic faster than 300 megabits per second, it will be dropped by the ISP, so I will shape the outgoing traffic to 300 megabits per second. There are various possible uses for shaping and policing, but this is a common use of these tools. Okay, that was a lot of material to cover. Let's review what we covered before moving on to the quiz. First, we covered classification and marking. Classification means identifying different kinds of traffic so that you can then treat it with an appropriate level of priority. Marking refers to setting the values of certain fields in the Layer 2 and Layer 3 headers for use in classification. We covered the COS field in the .1q tag, then the TOS byte in the IP header, including IP precedence and differentiated services code point. I also introduced the concept of trust boundaries. I then expanded on queuing and congestion management, which I introduced in the last video. I introduced the concept of multiple queues, weighted round-robin scheduling, CBWFQ, and LLQ. Marking a packet as EF, for example, doesn't actually do anything on its own. You have to configure tools like CBWFQ and LLQ to make the devices treat those packets as high priority. Finally, I introduced shaping and policing, which are both tools to control the rate traffic is sent or received. Watch until the end of the quiz for a bonus practice question from Boson Software's XSIM for CCNA. Okay, let's go to quiz question 1. Which of the following COS markings are consistent with standard practice? Select 3. Okay, pause the video now to select the correct answers. The answers are B, COS 0 for best effort, D, COS 5 for voice, and E, COS 4 for video. Here's that chart again showing the PCP values, which is another name for the COS values, and their traffic types. In your networks, you don't have to follow this marking scheme, but this is standard practice. Okay, let's go to question 2. What bit pattern would you find in the DSCP field of a packet marked as EF? Pause the video now to think about the answer. Okay, the answer is D, 101110. Here it is, showing the decimal value of each bit. EF, which is used for traffic requiring low delay, jitter, and loss, has a decimal DSCP value of 46, so the bit pattern is 101110. Okay, let's go to question 3. Which of the following AF markings provides the best service? Pause the video now to think about the answer. The answer is B, AF41. Here is the table of AF markings again. AF41 is in the highest priority class, and it has the lowest drop precedence. AF43 is also in the high priority queue, but it has a higher drop precedence. AF51 and AF61 are not real AF markings. AF only uses classes 1, 2, 3, and 4. Okay, let's go to quiz question 4. Which of the following statements represents general best practice regarding QoS? Pause the video now to think about the answer. Okay, the answer is A. Trust markings from IP phones. Don't trust markings from PCs. IP phones will typically mark their voice traffic as EF and COS 5, and those markings should be trusted because voice traffic requires low delay, jitter, and loss. Markings from PCs should not be trusted though. Traffic from data applications on PCs should be marked as low priority so that it doesn't fill up the high priority queues reserved for voice traffic. Now, apps like Zoom or WebEx used on a PC do need high priority service, but we can mark those packets at the switch or router. Okay, let's go to question 5. Which of the following creates a strict priority queue for data that requires low delay, jitter, and loss? Pause the video now to think about the answer. Okay, the answer is B, LLQ. Low latency queuing creates a strict priority queue, meaning if there are packets in that queue, the scheduler will always forward them next, before traffic in the other queues. Okay, that's all for the quiz. Now let's take a look at a bonus question in Boson Software's XSIM for CCNA. Okay, here's today's Boson XSIM practice question. Which of the following does RED and WRED address? Select the best answer. Okay, so these are the 4 options. Please pause the video now to select the correct answer. Okay, let's check. So which of these problems is solved by RED or WRED? Well, they aren't all necessarily problems. Strict priority queuing, for example, is a very useful feature. However, it can lead to this problem, bandwidth starvation. Now this can be addressed by using policing to control how much data goes into the strict priority queue. Now bandwidth guarantees, that's a part of CBWFQ. So you're guaranteeing that certain queues get certain amounts of bandwidth of the interface, even if the network is congested. Now tail drop, that's what happens when the queues get full and no more packets can enter, so they are dropped. Now I introduced this actually in the last video, day 46. RED and WRED drop packets early before the queues fill up, so they address this problem, tail drop. Okay, so I'll click on show answer, and that is correct. So here is Boson's explanation. I recommend pausing the video now to read it. Okay, and they also have a nice reference here to some Cisco documentation, Congestion Avoidance Overview. Okay, so that's a quick look at Boson Software's XSIM for CCNA. These are the best practice exams for the CCNA, so I highly recommend getting Boson XSIM to help prepare for the exam. If you want to get Bose.xim, please follow the link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. There will also be a packet tracer practice lab, so you can get some hands-on practice. Now, QoS configuration isn't actually part of the CCNA exam, and we didn't cover it in this video. But I think it will be beneficial to see how it's configured, so I'll do a quick demo. That will be in the next video. Sign up for my mailing list via the link in the description, and I'll send you all of the flashcards and packet tracer lab files for the course. Before finishing today's video, I want to thank my JCNP level channel members. To join, please click the Join button under the video. Thank you to Justin, Christopher, Sam, Anton, Tebogo, Samil, Anand, Pavel, Abraham, Sergey, Njoku, Victor, Roger, Raj, Kenneth, Seamus, Brandon, Marcel, Coney, Donald, Simode, Gustavo, Benjamin, Prakash, Nasir, Erlison, Marco, Daming, Ed, John, Funny Dart, Velvet Jacob, Mark, Yusuf, Boson Software, Devin, Lito, Jonathan, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. This is the list of JCNP level members at the time of recording, by the way, April 25th, 2021. If you signed up recently and your name isn't on here, don't worry. You'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.